what's coming up. First, I won't be here tomorrow or Friday. And so there's no class Friday. I will be available for Zoom meetings. So I'm available for Zoom calls Friday. Morning through about 2-ish. So if you want to talk, I'm happy to talk. Just send me a message and we can set something up and I'll send you a link. Okay?
So you going to Vegas?
I'm going to visit my wife's in-laws, and they don't live in Vegas. All right, any questions about that? So this is the last class for this class. And then the final is scheduled for the last day of finals week, Friday, 12:15 at 11 a.m. You know, like I just said in statics, for the people who are taking both of those classes, please feel free to contact me and we can work out something else so you don't have to take those back to back. Happy to do that. But that's the scheduled time. Anybody have any questions about the final? All right. Yes.
Will it include like super reading for ranking cycles?
Yeah, you should be able to do stuff like that. And I'll talk a little bit about that today. But okay, so yes, it's close enough to like it just doesn't add that much difficulty. So I'd say, yeah, I could put that stuff on there, but in the interest of time, I don't know. There's a good chance I would not, but yeah, you should be ready for that.
It's basically going to be celebrated.
Yes, that's right. That's all it's going to be is like a little longer. I can fit in maybe one more old question or something like that, you know. It's not going to be very long. Yeah. Okay, so now we're going back to the outline. We're just sort of slowly working our way through all the topics that we've covered. So back to the outline from last time. We had covered up through the first law, so now we're moving on to the second law. So part 4, the second law of thermo. So first of all, there are the 3 different statements of this law. And they're all equivalent, although it's not immediately obvious why they would be equivalent. The simplest one is the Clausius statement. The most confusing part about all this is that the Clausius statement is the least like entropy, but the Clausius inequality is where the idea of entropy, the entropy statement comes from. So there's these two different Clausius things, and they're sort of in different worlds in this area. But the Clausius statement just says heat can only transfer spontaneously from high temperature to low temperature. And then second is the Kelvin-Planck statement.
Is that the same Planck as like the really small? I think it's time. It's like,
Yeah, I do not know, but I always assumed it was, but I don't know. And then the third one, the one that's most important for us, is the entropy statement. Remember that when we talked about the Kelvin-Planck statement, that was when we talked for the first time about efficiencies of different power cycles and ideal efficiencies that are based just on the temperatures of the boiler and the condenser. And then after we talked about those, the first big result that came up was the Clausius inequality. And this was the first kind of hint at like how much subtlety there is to this stuff. And it's hard to keep all this straight, I know. But the Clausius inequality said, for any cycle, the integral of delta Q over T around the whole boundary is, what does this inequality say? Do you remember?
Greater than 0.
Almost.
Plus.
You're thinking of negative this, but not really. You're not thinking of shit.
I was close.
Yeah, it was all right. You had an inequality, but I mean, I just bring it up because it's hard for me to keep this stuff straight too. But making sense out of this makes the stuff that comes later clear. So it's worth taking the time to try to straighten this out in your head, I think. And then, what would it mean if this was not an inequality? It was an equality.
It would be.
When would it be equal to 0?
It's always reversible.
Yeah, internally reversible, yep.
I'm trying, guys.
Yeah, right idea. Okay, and the thing to remember about this is that this is for an actual process, okay? I mean, I guess what I wrote in red sort of makes that clear. But so we're not talking about a perfect thing, we're talking about actual processes. If it is a perfect thing, then it's equal to 0. Well, that equality kind of hints at the fact that entropy is going to be a property, because if you have a cycle, then any property ends up back where it started again. Okay, so what this says is, if you start at some point, cycle all the way back to it, this thing that we're going to call entropy later is going to have no change. You know? Yes.
wait, didn't it say greater than or equal to 0? I swear to God, I've seen the other way around.
The greater than or equal to 0 is if you add up all the change in entropy.
Oh, I see.
Yeah, I know, that's the kind of stuff that's so confusing about this.
Yeah.
But if you take all the changes in entropy for an isolated system, you have to have greater than or equal to 0 entropy. But this is the opposite. And so what this gives us is, we're going to get to it in a second. Okay, so C. The definition of entropy comes from the fact that the change in entropy is equal to the integral of that same sort of funny ratio for an internally reversible system. Well, what would the change in entropy be for a cycle? That's what I was just saying, is that since it's a property, a full cycle brings you back to the same state you were at before, so there'd be no change in entropy for a cycle. On the other hand, for an actual cycle, if you're doing this calculation, you're going to get something less than 0. Okay. Okay, so now combine those two things. Yes, sigma, but yes, exactly. Combining B and C gives this form of the entropy statement, this form that was really useful to us. And that says that the change in entropy is equal to the integral of dq over t around the boundary plus some sigma. Okay? And this has to be positive or 0. And this is for the actual process. Well, if this wasn't for an actual process, if this was for an internally reversible process, then you have the definition of the change in entropy. So obviously those two sides would cancel each other and sigma would be equal to 0. Okay? Yeah.
So online, sometimes people define entropy as like the measure of disorder of the system. Would that be accurate if there isn't any like heat transfer involved at all in any kind of like activity?
Remember, we talked about isentropic stuff where the entropy doesn't change, and that does require that there's no heat transfer. I mean, if there's no thermal activity at all, then you're at absolute 0 temperature, and then you're at 0 entropy.
So I guess if the heat transfer is like negligible or it's just not big enough, would it be an accurate statement to say like it's a measure of disorder?
Yeah, so to me, here's how I think of the disorder thing. Think of entropy as kind of like, so there's always like an amount of thermal energy in something, like anything you have, there's thermal energy. And entropy is measuring how bad that thing is, how bad that thermal energy would be for trying to create, for trying to power, to try to create a power cycle using that thermal energy. Okay, so like if you have, so there's a fixed amount of energy in the universe, how would you have the absolute least entropy, You would have the absolute least entropy for that energy if all of that thermal energy was in one place that was 50 quinzillion degrees, and then everything else was at absolute 0. Because you could create a great power cycle out of that, you know what I mean? the efficiency of a power cycle comes from having a really high temperature and a really low temperature. But as you start letting those two things blend, so say the first little bit of energy that goes from your hotter than the sun temperature into absolute zero, that energy that you put into the really cold part, that's going to be really hard to get back as work in a power cycle. Because in order to use that energy in a power cycle, you have to find something colder than that to transfer the energy to. You understand what I'm saying? And how are you going to do that, So basically that first bit of energy that goes from the sun to absolute zero is like gone forever. And that's sort of what the idea of disorder with entropy, that's kind of what it is. Like, it's saying, when you have the super hot and the super cold, everything's really well organized.
Yeah.
There's like perfect order. As you start letting the heat transfer to the cold areas, it's going to be really hard to get that energy back in any useful way. That's the idea. Remember, you guys don't because you're too young, but McDonald's used to have this thing called the McDLT, where they gave it to, probably the not being allowed to use styrofoam is what killed it, but they gave it to you in two halves, the hot side hot and the cool side cool. And then you folded it together. So like, the lettuce and tomato are like nice and cool. But it was like they're like low entropy hamburger, Like it was ready to be a heat engine until you folded it together, So anyways, I think that's kind of a reasonable way to think of when I used to always be confused by that. Like, what do they mean disorder? Well, that's what it means. Like if you have high order, the energy is very separated in a way that you can get useful work out of combining them. When the order is very low, it's very disordered. Everything is like eventually, what do they call it? The thermal death of the universe. Yeah. Eventually all the hot stuff will have blended with all the cold stuff. Everything will be the same temperature and then there'll be no work available anymore. But that's still a long way away, so don't worry about it. Yeah, exactly. That's not till like April.
That's before finals.
Yeah. Yeah. Yoo-hoo. No studying. All right, so this thing is a statement of the second law of thermodynamics, one that's useful. It's useful because if you can figure out what that produced entropy is, it can tell you something about your efficiency. You want that to be small if you're building something that's efficient. And we'll get back to other forms of this sort of thing. Next was the TDS equations. These are very useful for calculations. We always dealt with them in pretty simplified cases, but a lot of the values in tables come from using the TDS equations. The key thing about this is that they always hold. So remember that you can always, if these help you, they're always available. And there are two of them. TDS is equal to du plus PDV. And TDS is equal to dH minus VDP. And even, for us, we derived a lot of useful things from these. One of the things that we derived from this, part F, was deriving expressions for the change in entropy for incompressible materials and ideal gases. And then from our expression for the change in entropy for ideal gases, we came up with this idea of isentropic processes for ideal gases. So this thing I'm about to write down comes from those TDS equations. So this is isentropic processes for ideal gases. What it requires for an isentropic process is that there's no heat transfer. And that the process is internally reversible. There's no reversibilities inside the system. And we saw this two different ways. The first way, the easiest one to use, if you can use it, is if there's not too huge of changes in temperature. You get 0 is equal to C sub P times the natural log of T2 over T1 minus R times the natural log of P2 over P1. So you can use knowledge of two pressures to get a temperature, a beginning or ending temperature, or you can use knowledge of two temperatures to get a beginning or ending pressure. And then there's another form that just comes from the other TDS equation. 0 is equal to CV times the natural log of T2 over T1 plus R times the natural log of V2 over V1. If the changes in temperature are too big for this to be accurate, you can also use values in an ideal gas table. So P2 over P1 is equal to P sub R at temperature T2 divided by P sub R at temperature T1. Those PRs are values you can just look up in the table. And you can also come up with a ratio of the volumes with a similar idea. V2 over V1 is equal to VR over T2, VR of T2 over VR of T1. The PRs and VRs are just things you can look up in the ideal gas table. And then the last thing that we talked about for the second law was, so this is the second law for control volumes. And that said ds dt for the control volume is equal to the sum of all the Q dots over temperature around the boundary. Everything here is a rate. Plus m dot at the inlet times specific entropy at the inlet minus m dot at the exit times specific entropy at the exit plus sigma dot, and that is, this sigma dot has to be greater than or equal to 0, and that's the rate of entropy produced. And that value for the rate of entropy produced is useful the same way as our entropy produced was in the closed form, this sigma here, for just helping you find where inefficiencies are. If you have a very inefficient system, that value is going to be small, but it always has to be positive. Can you remember any problems? We did 1 or 2 problems using this. Do you remember what kind of stuff you can do with this? I remember one of the things that we did with it was we used the control volume first law to figure out something about a device that I said was either a nozzle or a diffuser. And we calculated using the first law what the values are, say the output speed or something like that, the exit speed. And then we ran it through this to figure out, okay, which one is it, a nozzle or a diffuser? Remember that the second law is always something you can use it's the only tool we have to figure out the direction in time that a process is moving. And so like what we did then is we assumed it was a diffuser, say, ran it through this. If you get a positive value of sigma dot, then okay, it's a diffuser. If you get a negative value of sigma dot, then no, it has to be a nozzle because it can't go in that direction in time.
Is this an exam question?
It's a good exam. It's a good thought. Yeah, that's all going through my head as I'm doing this. Like, what are the things? Coming up with exam questions is hard. Like, you don't want to do something obscure that just is going to be luck of the draw, whether it pops into someone's head or not, but.
So we all look blank when you're showing this, you're like, that's a good one.
Yeah, exactly. I'll get them back. But yeah, so second law, I mean, there were a few kinds of problems we did where we were trying to figure out using the second law what the direction in time was of a process, We did that with putting a hot thing in cold water and like show that it couldn't go in reverse. And we did it with something like this. That sigma can always tell you the direction in time of processes. Okay, and then the last thing we talked about was Rankine power cycles. And so first I'm going to talk about without reheating. So this includes the case with superheating and the case without superheating. Both of them work like this. You start here at state 1, go through a turbine to extract power. And that power is W dot coming out of the turbine. Then you get to state 2 and go through a condenser. And at the condenser, heat at a rate of QC dot leaves the system. then you get to state 3, and the working fluid goes into a pump. And at the pump, work is done on the system, WP dot. And then coming out of the pump, you're at state 4, and you get to the boiler or the steam generator. And at the boiler, heat comes into the system at a rate of QB dot. And this can look 2 ways on a temperature entropy diagram. If you have no superheating, state 1 is here. State 2 is there. State 3 is a saturated liquid. State 4 is the one that's kind of a pain because it's the only one in this cycle that isn't a saturated state. And if you have superheating, everything looks the same except that this point here is not state 1. This is state 1. Two, state 3, state 4, in order to calculate the efficiencies in both of these 2 cases, so the efficiency is equal to 1 minus H2 minus H3 over H1 minus H4. And this efficiency goes up as the temperature or the pressure at the boiler go up. Can you understand my notation there? That's kind of ugly, but this efficiency improves as the temperature or pressure in the boiler get higher. And it also, this efficiency goes up as the temperature and pressure in the condenser go down. And in order to calculate this efficiency, we'll use these 4 facts. So WT dot over M dot is equal to H1 minus H2. QC dot over M dot is equal to H2 minus H3. Anyone remember where we got these? Where we derived these, like WT dot over M dot is equal to H1 minus H2? We got those from the control volume first law. Then the pump. WP dot over M dot is H4 minus H3. And remember that the pump is the one that's kind of a pain because you have a compressed liquid that whole time. But this is the one where most of the time we're going to use the fact that this is incompressible. So this is also equal to the specific volume times the pressure at state 4 minus the pressure at state 3. So you can use either two of those. Either of those two. And then Q dot at the boiler over M dot is H1 minus H4.
These things you'll.
Yeah, everything here will be given. I just want you to notice here that whether there's superheating or not, all of this stuff is the same. The only thing that's different if there's superheating is you need one more property to know what's going on at state 1 because you're not at a saturated state. And then we talked about second. So we're still talking about these two cases where there's no reheating. Isentropic efficiency. This is the case where we take our, I'm just drawing this in the case of no superheating, but it works the same if there is superheating. But we first do this calculation for this ideal case where we have a state 1, a state 2S. So that's assuming isentropic turbine. State 3, state 4S. And then we piggyback on those results to get the true state 2 and the true state 4. And doing that is really easy. We just use this equation, two equations that say H2 is equal to the isentropic efficiency for the turbine times the quantity H2S minus H1 plus H1. And then for the state 4, H4 is equal to 1 over the isentropic efficiency for the pump times the quantity H4S minus H3 plus H3. So you go through problems like this exactly the same as if they are ideal, and then you just make these corrections at the end. Okay, so this is all if you don't have reheat. And the last thing we did was, well, what if you do have reheating? And this time, we have a state 1A here, a state 2A down here, 1B here, 2B here, and then 3 and 4, just like they were before. And the calculation of the efficiency is a lot uglier now. So we have W T1 dot over M dot plus W dot T2 over M dot minus WP dot over M dot all over Q boiler 1 dot over M dot plus Q boiler 2 dot over M dot. And those come from W T1 dot over M dot is equal to H at state 1A minus H at state 2A. WT2 dot over M dot is equal to H1B minus H2B. QB1 dot over M dot is equal to H1A minus H4. And QB2 dot over M dot is equal to H1B minus H2A. Okay, and that's a class. That's all you need to know about thermodynamics for now. Anybody have any questions about, I guess first, any of these Rankine cycle things? So always in the Rankine cycle things, all you're trying to do is find those enthalpies. And then any other just sort of general questions about things? All right, well, sounds good. So send me a message if you want to talk on Friday. And other than that, I'll put information about office hours for next week and stuff up on D2L. And I'll talk to you later.